Hello everyone, today I'm honored to present our paper, Athena Quantifying Side Channels, Analyzing and Quantifying Side Channels of Transport Layer Protocols. This is joint work with my collaborators, Zhou and Dr. Syed, Rafiul Hussain from Penn State University, and my advisor, Dr. Danfeng Zhang at Duke University. To start with, the modern network we are using today consists of several different layers according to the OSI model. Our work focuses on vulnerabilities within the transport layer protocols. For example, the most widely used application layer protocol is HTTP, and it's based on TCP. So attack against the transport layer protocols has been a very important thing to study, and researchers have been putting their effort on this for decades. Perhaps one of the most iconic transport layer attacks are the TCP hijacking attack and the DNS cache poison attack. So for example, if the attacker can learn the sequence number in your TCP header, then they may be able to take over your connection. And if they know the port number used for your DNS service, they may be able to manipulate what websites you are going to visit. Such attacks against vanilla TCP and UDP are still very important and worth studying today because there are still many cases these attacks are used without encryption like TLS, like in the initial handshake. Here's one illustrative TCP side channel attack to show how this works. We assume a traditional off-path attacker model where the attacker can neither modify nor eavesdrop packets in the victim connection. To launch this attack, the attacker first sends a reset packet to the server. This triggers a response ACK, and the server will lower a globally shared counter called ACK count by 1. In a second stage, the attacker can flood the server with 100 reset packets. If the counter has been previously lowered, then limited to this counter, the system will only send 99 ACK packet back. While if the initial reset packet contains an invalid sequence number, the server will instead ignore this packet and will not lower this counter. So in the second stage, the attacker will now see 100 responses instead of 99. Based on this observation, the attacker can launch inference attack on the sequence number. And by knowing the sequence number, as we just talked about, they can potentially hijack your connection. And in addition, it's noteworthy that such counters are actually stored as a file on Linux file system, so an unprivileged process can access this even more easily. So we consider these following two threat models in our work. The first is the traditional off-path attacker model, and we also consider one variant, the aided off-path attacker model, where the attacker, in addition to all the off-path capabilities, they have control to an unprivileged process on either or both of the victim machines. This figure shows the corresponding code of this side channel vulnerability. Pay attention to this branch. This is a secret-dependent branch. It's checking if the counter ACK count is positive or not. This will decide the outcome or the output of this program. So this is the root cause of this side channel we just mentioned. There have been a lot of work on studying transport layer security as side channels. One major limitation of the prior work is that they discovered side channels mostly by manual investigation. Given how large modern softwares are and how fast they can iterate, we think it's nature to come up with an idea to develop an automated tool to detect such side channels. While there have also been some automatic and systematic work on side channel detection, like there have been work using model checking and fuzzing to detect side channels within transport layer protocols. Due to their limitation on scalability, they could not cover either the whole code base or they could not cover the whole program states. Our solution to this problem is to model the detection of side channels as a graph search problem. This reduces the time complexity of detecting from exponential into a linear complexity, and thus provides great scalability, and it allows us to analyze the whole code base and all possible program states. Another limitation of your work is they lack the quantification of side channels. Side channels can be more or less severe. They can even affect the usability of a system, or they can be very minor, not even concerning. So such severity has been barely mentioned or reflected in prior reports. Our solution is to quantify and rank all these side channels by providing a ranking based on their severity. We aim to provide more insights for the developers who are going to fix them. We think this will greatly improve the quality and usefulness of our final report. Next, I'm going to introduce our workflow. We start with a set of source code files. We feed these code files into our static taint analysis, which generates one specifically modified graph called the tainted control flow graph. We then feed this graph into our leakage analyzer, which outputs a list of ranked branches. Then we used our designed replace algorithm, which we'll discuss later, to simulate the mitigation of these side channels on the original graph. We iterate until all side channels are reported and mitigated on the original graph. Finally, we aggregate all reported side channels into a single complete side channel report. This includes many useful information, such as a measure of their severity, the states or conditions needed to trigger the side channel, and many more. As we've seen once in the previous slides, this piece of code includes a secret dependent branch, which we call the sensitive branch. This is critical to side channel detection. If a sensitive branch can alter the outcome of the program, and such outcome can be observed by the attacker, this makes a side channel vulnerability. To find these side channels, our analysis works to detect a critical branch on a variant of CFG, which we call the tainted control flow graph or tau CFG. On the graph, we detected these critical branches, which are defined by sensitive branches that can reach one or more observable outputs. By doing so, we have transformed the detection of side channel into a graph search problem with great scalability. The motivation of further quantifying side channels is also very nature, since there are still a large number of critical branches on the control flow graph. In this example, we can see there are two critical branches, branch A and branch D. However, we want to ask this question. They are both critical, but are they equally severe? The intuitive answer seems to be no, since branch A actually doesn't have control to the outcome of this program. Either side A will take, either it goes to B or C, eventually reaches D. So the outcome of A doesn't affect the outcome of this program. For an automated approach to tackle this problem, we introduce our novel measure of information leakage by the entropy difference. Information entropy measures uncertainty, so it gives insights on how much information that could be leaked at a certain program state. And entropy, the difference of entropy further measures how much a node or a branch can contribute to the overall leakage of a program. In this example, we can, after some calculation, we can see that branch D actually contributes more leakage than branch A in this example. This matches our intuition that D is the branch that's responsible for the information leakage, and it's not A. While in this case, it's quite obvious that this side channel is completely dependent on D. So when D is fixed, A no longer remains a side channel. But there can be some partially dependent case. Like in this example, while by intuition and by our definition, side channel B appears to be the more severe side channel than side channel A, but we still want to ask this question. If we fix side channel B first, then will A still be a side channel or not? This may be not a very hard question if we can examine the code by hand, but for an automated approach, we want to first look at how in real-world engineering, how do they mitigate these side channels. This is the piece of code in Linux version 4 to mitigate a counter-based side channel. We don't need to understand the whole code piece, but just pay attention to the underlined code that they have added randomized component to the counter. This does not eliminate the side channel itself, but it makes the inference attack much more difficult. So we want to mimic this behavior. So we designed a replace algorithm to simulate the mitigation on the graph. we introduce a special wildcard node, which is denoted by the star symbol here. Intuitively, the wildcard node represents a randomized state. It counts as a distinguished output, and any leakage below this point will not contribute to leakage above this point. More mathematical details can be found in our paper. After several iterations, we aggregate all reported side channels into the final one complete and classified side channel report. We have implemented our tool and evaluated it on several different benchmarks. These benchmarks include 2 Linux versions, also 2 most recent BSD OS kernels, and we have also covered 2 most popular open source implementation of TCP UDP on GitHub. The evaluation results show that our tool effectively reduced the number of candidate branches. Taking Linux TCP as an example, since the code base is pretty huge, there are over 1,000 sensitive branches in the code base. Our tool can first reduce it into a few hundreds, and then only 6 branches are reported to be the final side channel here. We also pay attention to the efficacy and precision of our results. We have uncovered a total number of 42 side channels, 30 of which appears to be new. We have also verified the proof work, and we find we can detect all non-side channels under the same star model. We also manually verified our results, and we found only 5 side channels appear to be false positives. To summarize, the contribution of our work is we are the first to model the detection of TCP UDP side channel vulnerabilities as a graph search problem, and we have designed and implemented this automated tool for detecting and quantifying side channels. Finally, we evaluated our tool on several different benchmarks, and we uncovered a total number of 42 side channels. Our code is open source as a linked list here. Be sure to check out if you are interested. This is the end of this presentation. Thank you all for coming and listening. Please feel free to ask any questions. I'm happy to take any if you have here or after the session.